Hello everyone, this is Mr. Willem. Today we are talking about section 2.6, which is the multiplication and division properties, and we're going to talk about applying them to proofs, dealing with segments and angles. The first theorem that we're talking about is if segments and angles are congruent, then they're like multiples are congruent. How does that look in a diagram? If we are given that BD and VE trisect angle ABC, so we have these three angles are congruent. We also have the same thing over here on this other diagram, on the other one, that all of those angles are congruent. We also start with that angle ABD on this diagram over here is equal to angle over here, which would then imply that all of these angles are congruent. We could prove that the bigger angles are congruent because if the smaller ones are congruent, let's just call it x, it would all be x. It would essentially be multiplying the entire angle by 3, which would give us an entire angle of 3x. So we're starting with the smaller angle is congruent, and we can get the larger angles congruent by essentially multiplying. So if two segments or angles, depending on the diagram, are congruent, then they're like multiples are congruent. In a similar fashion, we could do the same thing if we are going to be dividing. So in this case, we have trisect on both sides, but we are given that the entire segment is congruent to the entire segment down in the bottom. Then we are talking about going from a larger segment down to a smaller segment, saying that these two segments are congruent. So we are saying that they're like divisions are congruent. We know how to use multiplication and division instead of addition and subtraction if we are talking about a double use of midpoint, bisect, or trisect. That would be your clue that we're talking about multiplication or division. So when you see this double use of trisect, so we're trisecting each segment, therefore we're multiplying the segments or dividing the segments to get to our other pieces. In a proof, some of these proofs will be short when we're talking about multiplication division initially. In this particular proof, we have that the entire segment on this left side, DF, is congruent to GJ, and we have a midpoint on each side, which means that we are going to be able to cut each of the segments in half on each side. We first start with our givens, and in this case we can go directly to our conclusion statement because we are starting with the larger segments are congruent, and we want to go to the smaller segments of DE and GH, and we have our double use of midpoint. So because we're going from larger segments to smaller segments, we can say that if two segments are congruent, then they're like divisions are congruent. This next problem, we are looking at angles in this case. So we are talking about angle NOP is congruent to angle RPO. And again, we have a double use of bisect. So we are cutting each of those angles in half, and when we cut those angles in half, we are going to be left with angles 1 and 3, which is what we're trying to prove in this case. So we start with our givens. And after we list our givens, because we're going from angle NOP down to angle 1, and angle RPO down to angle 3, we're going from larger angles to smaller angles using double use of bisect. We can say that two angles are congruent, then they're like divisions are congruent. Go ahead and pause the video for number 3 and see if you can come up with the reason for this proof, if it's multiplication or division. In this problem, we are given that our ys and rsy, so we are given these angles down here, and we have the double use of trisect. We're trying to go to the larger angles, so we're going from the smaller angles to the larger angles with our double use of trisect. So because we're going from smaller to larger, we can say that if two angles are congruent, then they're like multiples are congruent. For number 4, we actually need to add a step above because we are looking at angles 1 and 6, and they are we're going to be getting into the angles on the inside because of bisecting angle DBC and angle DEC. We're going to need supplementary at some point, which means we're going to need to put the straight angle. So let's do the straight angle step right away. Add in angle ABF as a straight angle, and we can assume that from diagram. And why don't you go ahead and pause and see if you can fill in the reasons with the steps being guided for, if you can fill in the reasons for the rest of the proof. So angle 1 being congruent to angle 6, we can say is given. And if we look in the diagram, 1 and 2 are angles that form a straight angle. So we can say that those two angles are supplementary, which is the same as angles 5 and 6. So if two angles form a straight angle, then they are supplementary. And as we talked about a couple days ago, we have angles 1 and 6 are marked congruent, which is mentioned right here and right here. Therefore, the angles 2 and 5, which are supplementary to congruent angles, we can say that those angles are congruent. So the beginning part was really a review of the previous lessons, and then the concluding steps are what we've been talking about today. We have that angle 2 is congruent to angle 5. So if we go into our diagram and look, we have angle 2 congruent to angle 5. We have a double use of bisect for each side, and then we're trying to say that the larger angles of DBC and DEC are congruent. So because we're going from smaller to larger with our double use of bisect, we can say if two angles are congruent, then they're like multiples are congruent. Moving on to the last proof, this is a great review of actually the last two lessons with our addition, subtraction, and multiplication, division. I'd like you to complete the last proof before you come into class tomorrow, and that will conclude section 2.6.